Good afternoon, everyone. So welcome back to Essential Perturbation Theory and Asymptotic Analysis. Any questions before we get started? So let me make an announcement. Then there's a homework posted online. I would like for you to do this assignment in LaTeX. So if you don't know LaTeX, this is an excellent opportunity for you to learn it. I will supply you, if you wish, with a LaTeX template for the homework, but I want everyone to give it a shot. So if you don't know LaTeX, now is a good time to learn LaTeX and type your solutions in LaTeX. You can collaborate with other people and you can borrow templates if you want. And so if you really have trouble with LaTeX, shoot me an email and we can discuss it. But if you don't have a compelling reason not to, I urge everyone to learn LaTeX. Yeah.
One of the questions is this about plotting.
Yeah.
Preference for plotting software?
No, I have no preference. However, you can get a plot in there is good with me. That one's pretty open to interpretation. So whatever you do there should be good. But bonus points for the most interesting plots. Other questions? So most of you work with Mac or Windows. Some of you might work with Linux as well. Linux, there's free software for LaTeX environment. Same with Mac and Windows. Mac and Windows have some very nice GUI software packages for doing LaTeX, and they're free. So the simplest one, if you use Mac, is probably TechShop. So the TechShop, spelled TEXSHOP. If you do a web search, you can grab that package. I will share, as I said, I will share a LaTeX template for you. Probably I'll give you an example solution to show you how it's done. All right. So, and again, if you have a compelling reason why you can't learn LaTeX in the next couple of weeks, then shoot me an email and we can discuss it. If you need more time than the 2 weeks that's allotted for this homework set, you can also ask for some extra time. I'll be glad to work with you on that. So again, this is just so you learn the material and a good excuse to learn LaTeX. And one reason why I want to do it is because I'm going to ask for the submissions of the homework to be online only. So you can see that the submission is online through PDF. I suppose you could scratch it out on paper and then scan it and upload it as well. So, okay, but I really want to encourage you to take this opportunity. Someone's forcing you to learn the most excellent typesetting language that a scientist, an engineer, and mathematician could ever use or know. If you were alive in the 70s, like some of us were, and doing research, I was not, and came into the 80s and were introduced to this tool called LaTeX, you would probably appreciate it more than air. If you're a mathematician, scientist, or engineer. But others might not be so excited about it because you guys grew up with color television, right? Okay. Some of us, anybody remember not having color television? I didn't, my first television was not color. So.
Is it like I saw a research that if you watch television as black and white when you're a child, then your dream will be black and
wow.
And vice versa. If you watch color television when you're a little kid, your dream will be color.
I don't know. I've never thought about that.
We didn't watch that much TV.
Outside playing. All right, let's get into the material. Are there any questions about the material? Okay, if not, we're going to jump back into matching. And just to make clear, none of this material that we're discussing is stuff that I came up with. It's all derived from many other textbooks. And specifically, the one that I'm using for this stuff on matching is from the textbook by Miller. I think it's 2006. That one's fairly technical, a bit more technical than what we will be doing in this course, but his exposition of matching is the best that I found in all of the existing textbooks, the easiest one I found to read. But now you'll have my textbook, so, and that'll be even easier, I hope. All right, so matching, we had to pick in way of review, we had to pick these numbers, indices n and m, and expand the outer solution up to order n, and replace every instance of x with the variable w. Okay, so we showed how to do that last time. Then we expand these terms because these will require expansion up to terms which are order little o of phi m. So that's where the m comes into this part. So it's n here, m here. So you expand these terms up to and keeping order little o of m terms. And everything that remains is, which is not bigger than that, or let's say smaller than that, gets caught up in this net called the matching solution. We do the same thing with the outer solution up to order m. We trade variables. Z now becomes, or is written in the variable w. We have to do an expansions of these terms, as you'll see. And we're going to keep everything that's little o of epsilon to the n power. So everything that falls below that gets caught up in this net called the matching term. Now, the idea is that these two expansions are going to be equal to each other. So for each compatible choice of m and n, there is an intermediate scale eta. Remember the intermediate scale we introduced last time, which defines the intermediate variable, such that it sits between the delta scale and 1. This means, of course, that it has to go to 0 as epsilon goes to 0, but this one is much smaller. This one also goes to 0 as epsilon goes to 0, but this is bigger than this one, that scale. Such that for each fixed and finite w, these two matching terms that we generated are actually equal. And so we'll write the common value as just, so we drop the out and the in here. So the common value is just the y match. And then a composite solution can be written in the following way. You take the outer solution up to order n terms, the inner solution up to order m, and you subtract off this matching term because that contributes, you would get that term appearing twice. So to avoid overcounting, we're going to subtract it off once. Now this should produce a term, an expansion, which can then be compared to the exact solution. So remember, we have an exact solution, and now we can write the composite solution over the whole interval, CNM. And this should be less than something which is order epsilon to a certain power. I'm going to put to the power question mark. On the whole interval, x0 to x2. So remember, the inner solution only works on near the boundary layer. The outer solution works in the outer solution environment. They don't have, they don't both work over the entire interval. The composite solution is constructed so that it is valid over the whole interval of interest. And we get one approximation value out here, okay? So the power of this approximation, or the order of this as epsilon goes to 0, we'll discuss later on. And we'll discuss it actually through some examples. We'll try to figure out how this is going to depend on n and m. In general, it's a little bit hard to say, but we'll discuss that later. For now, we'll just say it's epsilon to something. Now, that uniformly valid composite solution is, as it's written in 3 different variables, but we can always bring that back to the variable x, which is the common variable. So remember that z was x minus x naught. It's a positive variable. And w is x minus x naught over eta. So I've got relationships to get between x and z in either case. So I can replace the z with this and the w, because I also have the matching equations, or the matching terms are naturally written in the intermediate variable w. And so I can do the replacement given here to get back into variable, the variable x. All right, so let's see how this works. That's the idea of all this jargon, is to have a mechanism for writing down our approximations for specific examples. And so that's what we're going to work towards. Before we get there, though, I want to talk about the width of the matching scale. So I'm going to define this parameter called W, or omega. Now, eta, as we said in the general matching principle, which is going to become a theorem for us later on, but not yet. So the eta variable always depends on n and m. So the way it's written, that principle, the way it's written, that should be somewhat clear, because we say for every n and every m, there exists an eta. So that means that the choice probably depends on n and m, and it will in general. So we're going to find that this difference is going to diminish in some sense. So typically the size of the intermediate scale, as I said, depends on n and m. And we're going to observe for fixed epsilon, once you fix epsilon, that the limit as n and m go to infinity of this thickness, I'm calling the width of the matching layer, or which width of the matching scale goes to 0. So this won't make sense yet, but we're going to come back to this whenever we do the following example, and we'll see what exactly is going on here. So let's do an example. So what example would we ought to use? Let's use our prototype. So we had this prototype boundary layer function that we saw as epsilon gets smaller and smaller, exhibits a boundary layer near x equals 0. So we can identify some of the elements in the matching procedure already, because we've done the asymptotic series expansions already. So for example, we know that the delta scale is epsilon. The boundary layer is the boundary layer is located at x naught equals 0. And the upper limit on x is equal to 1. The phi sequence, the asymptotic sequence phi that we use in the expansion of, I think it's the inner expansion, right? No, the outer, yeah. Sorry, inner expansion. We know that what that's going to be, it's going to be epsilon to the k. Okay, so it's the standard asymptotic power series. We showed that uniformly, actually, that the inner solution is asymptotic to e to the 1 minus x. In fact, we could show even more. We could say that the difference is transcendentally small between these two functions. And another way of writing that is to say that if we do an asymptotic power series expansion in the usual power series, that we get for y0 e to the 1 minus x, and y1 and all higher order terms, higher order coefficients in the expansion are all 0. Okay. So in this asymptotic expansion, we have these coefficients. Does everyone recall that? Questions about that? Okay. Now, for the inner expansion, we define the inner version of the function to be that part of y, or that version of y where we replace x by z epsilon. And so we get this function. Okay, so everywhere, remember, z is related to x by x over epsilon, so x can be replaced by z epsilon. If I do that replacement, then the not the singularity, but the boundary layer, the boundary layer nature in this term goes away. It just becomes a regular term. And so with this as our inner function, we did an asymptotic power series expansion. Here, we note that in this example, and not all examples are like this, but most of the ones we're going to be dealing with, phi k is equal to epsilon k. And the same, that is the same power series or the same asymptotic sequences used in the inner expansion as in the outer expansion. That's going to be the most standard case. Well, we showed that the inner solution, or the inner function, has the asymptotic series approximation or asymptotic series expansion given by or with these terms. So we showed that y0 is different than all the rest. y1 up to, all the ones greater than, and all the ones greater than 1 follow a formula. So the kth one is e, so that's our constant e, 2.718, blah, 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 minus 1 to the k, z to the k over k factorial. So those are our coefficients in our expansion. So we have everything we need to test out our general matching principle. So all we're going to do with this example is to check to see that the matching principle that we just laid out is actually valid. Yes.
On the last page, was that the expression for y inner approximated by e to the 1 minus x? I thought that was the outer solution.
If I said yes, this is a typo. That should be outer solution. I've got it right down here, but this is incorrect at this spot. Okay, thanks for the typo. All right. Right, so these are the terms, coefficients in our asymptotic power series expansion. We already have that. And so now it's just a matter of checking. So we're going to start out with n equals 0, m equals 0. And so we're going to start by computing this matching function. And you'll see how what's that?
Someone raised their hand.
Okay. Someone have a question?
Yes, on the y1z, what happened to the -1?
Okay. All right, so are you saying this one should be e to the -1?
No, so the y1z, it has, if you follow the yk example, shouldn't that be negative?
Let's see. That may be true. Maybe I've got an error here. Maybe it should be k plus 1. The chances are I copied this from somewhere else, so I may... Well, let's go back and see. Maybe this is minus. Let's see here. Okay. Yep, I copied. So the question is, what's the correct answer? Maybe it's maybe this is supposed to be k plus 1. Yeah, because it should fit the same pattern. So I'll check on that. I hope it doesn't screw up what I'm about to show you, but we'll see. Because now I have no idea what the true solution is. Okay. So let's compute this guy first. And this one I'm pretty confident about. So how do we do this? Well, all we're going to do is we take y0, and of course, times phi0, but phi0 is just 1. We sub in the variables w and eta. Okay, because that's just equal, that's x, right? So we know that w is equal to, in this case, x minus x naught, but x naught is 0 over eta. So eta times w is equal to x. So we sub that in. All right, and now we're going to try to generate this term by expanding up to terms which are little o of 1. All right, so here's how we're going to do it. So we sub that in for our y naught. Y naught is just e to the 1 minus x. So this becomes e to the 1 minus w eta. So we only have to expand this term. So let's do a let's do a regular Taylor series expansion of this term. So we should get this power series expansion, but we only have to keep up to little o of 1 terms. So all of these are little o of 1, so we really only have to keep this guy. Okay, so how do you check that all of these are little o of 1? So that little o of 1 means that if I divide by 1, I should go to 0. So let's check that. So we need to have, if this term here is really little o of 1, we need to have, as epsilon goes to 0, divided by 1, that has to be equal to 0. But w is fixed. W is a number. So we'll keep saying that over and over again. W is fixed and finite. We know that eta goes to 0 as epsilon goes to 0. So this guy is clearly O1. And we can check that all of these higher order terms are as well. Okay. So this is, again, is fixed. This guy is going to go to 0 even faster. And so we definitely are only keeping the order 1 terms by just keeping this guy here. So that's just this product. Okay, so that means that the matching the matching function is just this. All right, now you may remember that when we were in chapter 1 and we did what we called simple matching, we did matching by just including a simple limit. Though that limit turned out to be e to the 1. And that very simple matching procedure was basically like saying that the 0-0 match terms have to agree. All right. Okay, so let's move on then. And by the way, this order 1 has to be order 1 as epsilon's going to 0. So if you go back to the definition, you can check that. So that's why we had this limit going here. Okay, everything's cool though. Now let's go to the capital Y0 term. So what was capital Y0? Well, first of all, let's review what we need to do. So we have y0, that's naturally expressed in z. We're going to substitute in w because we need to work with w. So how do we get from the matching variable to the intermediate variable? Well, we do that through x. We know that we know that z is equal to x over epsilon, and we know that w is equal to x over eta. Okay, or I guess in general it's delta, but we know that delta is equal to epsilon. All right, so that means that z has to be equal to w times eta over delta. So you can just, for example, solve for x here in terms of z. Z is epsilon or delta times z, and so you get it from that step there. So we have to sub in the variable, or we have to sub in a form that uses the variable w. So we're going to do the same thing. We're going to expand, and we're going to keep terms, all terms which are less than little o1. All right, so remember delta is equal to epsilon. Here is our expression for y0z. So when we substitute in z, z was this part right here, right? Or this was minus z. So now what do we do with this guy? This guy, eta over epsilon. What do we know about eta over epsilon? Where is it going? It doesn't go to 0. So what is the limit as this guy goes to, epsilon goes to 0? This is infinity, right? Right, because we said that the limit as epsilon goes to 0 of delta over eta is 0. Delta is epsilon, so epsilon over eta is equal to 0, right? This one is the one that wins or dominates going to 0. So it's like if if eta is a power of epsilon, then it's like power 1 to power 1/2. Okay, so the power.
I have good news for you. Your YK formulation is correct, but your Y1, your calculation is wrong. It's not E, it's actually negative EZ. So
Okay. So minus EZ.
it's not easy.
Not easy, right? Nothing's easy. Okay, so we'll see how that works out. I probably
This is negative. When you
yeah.
When you do L'Hopital's rule.
I do. Okay, we'll see. Hey, sign amongst friends, it's not a big deal, right? Plus or minus. Okay. Right, so what then do we know about this term as epsilon is going to 0? If this guy is becoming large, e to the minus large is transcendentally small, right? So we know what transcendentally small means. That means it's going to be basically it's not going to register in terms of our scale functions. So I claim that this guy is just going to be e to the 1, or just e, plus O of epsilon. Where is this coming from, by the way? Oh, yeah. Epsilon over eta to the power r for any r. That's what we mean by transcendentally small. Okay. Epsilon over eta, is that small? Yeah, that is small. That's going to 0. So now I claim that that's an order 1 term as epsilon is getting small. You can check that detail. Okay, so how do you show that? Okay, maybe we'll check it together, right? How do we know that this is going to be order 1? What do we need to show? all we have to compare is the limit as epsilon goes to 0, e to the r, a to the r. We can take it to be 1 if we want. Over 1 has to go to 0, but of course it does. All right. So all of these terms that you could save any one of them that you want, they're all going to be order 1. Okay? Because they all go to 0. As epsilon goes to 0, for W fixed. So what do I know then? The matching solution for the inner problem is just going to be e to the 1. And so what did my general matching principle say? These two have to agree. And they do. Okay, I didn't have to make any adjustments at all about my value of, or the size of eta. All that I had to assume is this property here. Okay. So for example, I like to think about what works and what doesn't work. So we know that delta is equal to epsilon to the 1 power. So what could I take for my eta? I could take eta to be epsilon to the 1/2. That works. So what we're going to show is that as we keep changing n and m, this guy always stays the same, but this guy is going to move around. Okay. This guy might not be able to be satisfied by 1/2 anymore at the next step. So we'll check that. Okay. So the matching terms agree, and therefore we can make a composite solution. Our composite solution, the 0, 0 composite, is going to be the outer solution plus the inner solution. We're writing the inner solution back in the variable x, and then we're going to subtract off our matching term. This is exactly the same composite solution that we generated in chapter 1. Well, I didn't call it 0, 0 there. I think I just called it 0. So if I collect all terms, then I get, writing it over a single denominator, I get this. It turns out I'm always going to get that. Interestingly, I'll get more and more terms agreeing in my matching, but they'll always subtract off of something else so that I always just get this. So that we'll be able to show that as we do higher and higher order matching, we don't get any better approximation. This is not the general case. This is just this case specifically. Okay, so let's see that. Let's calculate the n equals 1, m equals 1 term. Okay, n equals 1, m equals 1. So remember I said we asked the question, how do we choose n and m? Or what should you do? The standard practice, especially when the asymptotic series that you use are both power series in integral powers of epsilon, then you generally choose n and m to be the same. You just always take them to be the same. And you start with 0, and then you go to 1, and then you go to 2 and 3. However, you can jump right from, instead of doing 1 or order 0, 1, 2, you could just do order 3 right away, and you'll see exactly what happens. Now, well, yeah, I'll leave it at that for now. You can jump ahead, but it's instructive to go one at a time and sort of move up. Notice also there's something different between what we're doing now and what we did in chapter 1. In chapter 1, we constructed solutions using the differential equations and using boundary conditions. So remember, the outer problem was completely determined. The inner problem was determined sort of halfway. And every coefficient that we derived, y0, y1, so on, always had a free parameter. And the free parameter was found via matching. Here, we're working with the exact solution, so there aren't any free parameters anymore. We know the exact solution in complete detail. right? If somebody gives you an analytic expression for the solution or the function, you know everything you need to know about it. So there's nothing free here. But the typical way we're going to use this, we're not going to know the solution of our boundary layer problem, right? We won't know the solution of the boundary layer problem. We're going to use matching in order to determine that solution. Okay, we solve an OD problem in the inner solution region and one in the outer solution region, and then we sew them together using matching, and it's the matching which determines any unknown or free parameters. All right, so let's compute this matching term y11 out. So, so what we need to do is take this two-term approximation to the outer solution, we rewrite it in the W variable, and then we expand, keeping W fixed and assuming that eta is small.
Can I ask a question of
Sure.
equation 21? Yes, here. So you say next we're looking for an asymptotic approximation of the form y0z equals to delta. Why we know that we are looking for this solution plus a small O1 term instead
That's
of
because that's the definition of this. This is defined as it's whatever you get when you do expansion plus little o of phi. It's either phi 0 or epsilon to the 0 power.
oh yeah.
That's by definition. Yeah. So in either case, phi 0, epsilon 0, it's just, those are just one. Any other questions? All right, so now we're looking for, we need to look for an expansion up to order epsilon or little o of epsilon. So, but like I'm getting a little ahead of myself. So we start with this expansion, right? This two-term expansion. This is 0, right? We showed earlier that that's 0, so that contributes nothing. And so basically we're always working with this guy. We sub in W, and then we do an expansion. We're just going to use Taylor again and again. And all we really need to know is where to stop in this expansion and what to keep. Okay. So let's do a Taylor series expansion for eta small, keeping W fixed, right? And so what we get then is this expansion like that. And I've expanded up to order little o eta squared. So by the way, so if you keep the power series expansion or the Taylor series expansion to eta squared here, then the next term is going to be little o of eta squared. You could also write this in another way. You can write it as big O of eta cubed. Okay. That's when you do Taylor. The remainder, so basically this is just saying the remainder term is big O of eta cubed as epsilon goes to 0, or little o of eta squared, okay? That is whatever the previous term looks like as epsilon goes to 0, okay? So that's what I'm doing. This should be equal to e to the 1 minus e w eta plus order epsilon. So what I'm claiming is that this term is order epsilon. I want it to be order epsilon. And you'll see why I want that momentarily. Okay. So this is going to be little o of epsilon if and only if, for W fixed, by the way, as epsilon goes to 0, provided that eta squared over epsilon is equal to 0. That's what that would mean for this to be order epsilon. Okay.
So another 1/2 power percent.
Yes. So now the 1/2 power is not going to work because if we did use 1/2 power, we would get epsilon over epsilon, and that would be 1, an order 1 limit. So what does it have to be? What would work in this case? we need this power to be, if eta is going to be a power of epsilon, we need it to be bigger than epsilon, or bigger than 1/2, right? Right? Because we need whatever we square, we need to be bigger than 1. Does that make sense? So we need to choose something maybe like alpha, just a little bit bigger than 1/2, so that when we square it, this guy is going to give us a power which is greater than 1. And that will force this guy to be 0. So this is a choice. This is a choice I have to make in order to make my matching work, as you'll see. When we do the n equals 2, m equals 2 case, I'll do it in reverse order. I'll do the outer expansion first, or sorry, the inner expansion first, and you'll see immediately why I'm doing this procedure here. So let me foreshadow and say, well, the reason why I'm stopping here and trying to force this guy to be order epsilon is because I know I only want to keep 2 terms. Whereas before I kept 1 term, now I want to keep 2, because that's the only thing that's going to be able to work to match my 2 terms in my inner solution. So I'm making a choice that I want eta squared over epsilon to go to 0. And that, if I choose a power for eta, is going to be restricted so that that power is bigger than 1/2. And that's what we mean by the width of the matching layer is going to start to diminish. So we had no restrictions in the n equals 0, m equals 0 case. But now we see that alpha equals 1/2 if we choose eta equal to epsilon to alpha is not possible. Because in that case, we would get an order 1 limit. So what we really need is alpha bigger than 1/2, as I just mentioned. Alpha is bigger than 1/2 if we take eta to be epsilon to a power. And that's the most natural thing to do, taking epsilon to be a power. So what will work is alpha to the 2/3 power. And I'll keep stepping it like this, just so that you can see what's happening. But look at the pattern. So alpha, the power I'm going to have to take is going to be n plus 1 over n plus 2. That one always works. I don't have to take it to be that sharp, or that sharp or loose, or whatever you want to call it. But if I take it always to be n plus 1 over n plus 2, then you'll see it's always going to work. Okay. So in this case, as I was arguing last time, whatever remains is going to be little o of epsilon, because when I divide by epsilon, I'm going to get the limit 0 if I make this choice here. Okay. I know that to get that choice to work, choosing alpha to be 2/3 will make it work. Okay. Then what remains is always going to be order epsilon. Sorry, little o of epsilon. Usually when you say order, you mean big O. So that's why I'm having to correct myself over and over again. Little o of epsilon. So what I'm concluding is that this expanding up to little o of epsilon is e to the 1 minus E1 W eta. Okay. And of course, as always, W is fixed and finite. And in this case, it's always positive as well. So our inner match, or sorry, I'm going to keep screwing this up. Outer matching solution is E minus EW eta. Okay, just whatever I collect here. And of course, I forced that to happen. I could have taken another term if I hadn't been so forceful with my choice, but I really just want these 2 terms. And now you're going to see why. You'll see why with n equals 1, m equals 1. And I see what happens with my y1 term here. So I fixed the sign on that, right? I screwed up the sign when I wrote it down. It should have been minus EZ. And so I fixed it here. So That's good because it worked out. I would have been baffled that it worked out otherwise. So,
Technically, you made two mistakes and they can.
yeah. Well, yeah. So what do we want to say? YZ should be minus EZ. That's the correction, right? Because I think before I said it was plus EZ, but it should be a minus. So I think it was Kathleen that pointed that out, and so she's correct. Now, this term y1 here is not generically equal to 0 like it is in the outer case. Okay, there's something there, right? Namely this. I have to multiply that by epsilon. Notice there's an epsilon that appears here. You really do have to do the two-term expansion of the inner solution. But I have to replace z with w variable. Y0 replaced with the w variable is just this. We've seen this before. We already know that this term here is not going to contribute because it's transcendentally small. So every time you write it down, you can basically just ignore it. However, this guy will contribute. You get an epsilon cancellation here and here. And so I knew that for my two-term expansion for the inner solution, I was going to get these terms plus something which is transcendentally small. So that's why I made the choice in the previous step to restrict the size of my matching. Okay, restrict the size of the epsilon in the choice of or the power of epsilon when I take eta to be some power of epsilon. Because this is going to be small to any order, okay? Small to any order. So this one I can show is going to be order epsilon. So as epsilon goes to 0, you should confirm that, okay? Let's see. Well, I actually want to confirm it now, right? So let's just say we keep the O of epsilon eta. And is this really going to be order epsilon? Well, if it really is, see, I may have to use one of the higher powers, right? Let's see here. I might need to refine my argument here a little bit because I know that this is limit. If I only keep epsilon to the first power, I would need in my claim that should be order epsilon. So if I divide by epsilon, so then I get what? Just 1 over eta. That's going to blow up on me, right? So let's see, what else can I do here to rescue this? Let's see if I take, do I have to take this as a higher order or what? So let me try the square. Remember, it's little o of any power, so I can keep trying the ones until I get the right one. But let's try this one. So this one is going to be I think I have to refine the argument a little bit here. So what did we say about eta? So we said that eta should be epsilon to the 2/3 power or better. So what am I getting here? So that would be epsilon 1 minus 4/3 also not going to work, right? So I need to keep going. I need to push it, right? The good news is this is little o to any order I want to choose. So eventually one of them is going to work, right? Does everyone get that? I'm trying to show that this is little o of epsilon, but that means I have to be able to, when I divide by epsilon, okay, so what I wrote is correct, but the means of proving it is a little more than I thought. So I'm glad we actually looked at this. So what do I need to take in order for this to work? So will the cube work? The cube would work, right? So let's take, so what I'm going to do is I'm going to say, I'm going to look at this equation that I have here, but the term that I'm going to use to show that I have little o, I'm going to use the fact that this guy is little o for any r that I want. So I'm going to take a to the r, or sorry, a to cube, right? Now let's show that that term is actually little o of epsilon. So what would I have to show? Have to show that limit as epsilon goes to 0, epsilon cube, eta cube, over a to the 1. So eta we said we can take epsilon to the 2/3 power, right? So that's going to be epsilon squared. I think actually I have to take one more. Okay, let's try it. That gives me 1. But luckily, every one of them works. Every darn one of them works. I want that to be 0. Is it going to give me 0? Okay, so I get epsilon cubed
Yes.
minus, what do we get? 8/3. Okay, and that finally works. But the thing that rescued me is the fact that this is smaller than any power. Okay, so eventually I got it. Is everyone okay with that? That's the sort of thing I have to check to make sure. Now, why did I have to push it to this term? Well, that's what the matching term is by definition. Okay,
I have a quick question.
sure.
So, let's say I don't have the mental power to guess and try and error. Can I, let's say I assume eta to be epsilon to, let's say, alpha. And then we know that from the previous, we know it has a low bound. And then also we know that R can be any number, so we have another variable R.
Mhm.
Can I sketch like a R plane and then sketch like a feasible region of it? And I know that I can pick a region.
I think so, yeah. I think that's essentially what we're doing.
Yeah.
We're not doing it very systematically. Yeah. Okay. So again, all this discussion was that we want to refine things so that we can show that whatever we have left is order epsilon. Now you think about it, eta is going to be some epsilon to some power, and that power is going to be, we're seeing it's strictly greater than 1/2 in a certain case, and it's strictly greater than 2/3 in a certain case. We may have to push that and push that and push that. But ultimately, we can choose an R large enough so that we're going to get the convergence we need. And the thing about R is any positive number too, right? So you're not just restricted to integer powers either. So we could have chosen this R so that we just get the one that the first one that cancels with this. Although 9/3 beating 8/3 is good enough, right? So this is our matching solution. And of course, they agree. Which is exactly what the matching principle says. It just says you may have to keep trying and keep refining, but you can find that they agree. And as we do this, we notice that we're going to have to keep choosing in the selection of our eta, we're going to have to keep pushing alpha larger. So it's going to climb up to 1. Well, remember the delta scale is already epsilon to the 1. So that's what I meant when I said the width of the matching, or what did I call it? The intermediate scale is diminishing. Okay, the difference in these two powers, alpha and 1, is going to get smaller and smaller and smaller and smaller. But I got ahead of myself again. All right, so we showed that the matching term's that. How do you produce a composite solution? Well, you just take the outer expansion and the inner expansion, and then you subtract off the matching. Okay. And again, notice we don't do any better. So all that work for no gain. No effective gain in the composite solution. Okay, the composite approximation is still as good as it gets. And again, so the question in the back of your mind should be, you said that you get a composite approximation. And if I subtract it off from the true solution, then I should be able to show that this is some order of epsilon to some power. And that should be increasing as we go along with matching. But here, we're not. We're clearly not getting any better as we match along, right? Well, the reason is maybe clear to some of you. Why do you think that we're not getting any better? How big is the difference between these guys already? The difference here as epsilon goes to 0 is already transcendentally small, right? So you can't really expect to gain any powers. All right. So we could have shown from the very beginning that we're epsilon to all orders for this guy, because it's there's a transcendentally small difference between the two. Okay, the difference is transcendentally small.
This depends on kind of like a higher knowledge about what C1, right?
Well,
We
okay,
need
so
we need to know it's transcendentally small so that we cannot gain power.
right. So we know, because we know what the true solution looks like. So here would be a tip-off if you were doing a computation, though. If you were doing a computation, you didn't know that you already have a transcendentally small approximation at order 0, then probably what's going to happen is exactly what you see happening here. You're never going to improve. Yeah.
So that should be like if I'm doing in practice, I just realized when I increase the power, I have not, my expression is not changing.
It's not changing, then that
Probably
means, yeah. Well, actually, I think that's basically a theorem that you can show. If you believe that, well, there are under certain assumptions, that's a theorem you can prove. Okay. Not for the solution of nonlinear boundary value problems. That would be a bit of a stretch, I think. But for linear, there's a theorem there.
Is there a name?
So there's a there's a theorem named after a Dutch mathematician from the 60s who proved a result in the 60s. I can't pronounce his name. Otherwise I would tell you.
Mr. German.
Yeah, Dutch, but yeah. All right. let's do the n equals 2, m equals 2 case. This is getting fun, right? So, n equals 2, m equals 2. This time we're going to start with the inner solution. And that will tell us what we need to do for the outer solution. So, inner solution, we've got the 3-term expansion now. And we're going to sub in the approximations or the variable involving w in replacement of z. Notice that we have epsilon to the 0, epsilon 1, epsilon squared. Okay, so I did get the sign right this time again, so that's good. The second order correction term is like this. Of course, we're going to get cancellation of epsilon here, cancellation of epsilon here. And so pretty clearly, what we get is this 3-term expansion, where if we only keep 3 terms, plus a term which is going to be little o of e to the r, a to the r for any r. And again, my argument is going to be the same as last time. Since this holds true for any r, I can take r and I'm going to assume that eta is epsilon to some power, which now we know is going to be bigger than a half and probably bigger than 2/3. Eventually I can take r big enough so that this guy here is going to be little o epsilon squared. All right, we'll make a choice here and then let's come back and check that in a moment. Okay. As I don't want to say something that's completely wrong, but I know this is right, so it must be the result's right, so we must be able to argue somewhere that it is. So what we get is I'm missing a term here, so that's a typo. This should be plus y2z epsilon squared. Okay. So I'm missing that term there. So when I did that 3-term approximation, of course, we took care of the transcendentally small stuff. These terms didn't actually need to be expanded because they're so simple. They're just simple powers. So notice that. Remember I said earlier we have to do expansions. Sometimes you can get away with not having to do expansions in the case that you have a simple power. This one, if you do an expansion, you'll see the transcendentally small nature of it. So that means that the matching term, the 2-2 match for the inner solution, it has to be this 3-term expansion. Is everyone in agreement with that? Okay. Now let's go to the 2-2 side, or the 2-2 match for the outer solution side. So we've got 3 terms, but really there's only one because y1 and y2 are both 0. So we have this Taylor series to expand. We're going to expand it, and we know we're probably going to need to keep the first 3 terms, right? Let's see. Make sure I have all this correct. Actually, yeah, just these 3 terms, not this. So I claim that this term here and everything above it is order epsilon squared, little o of epsilon squared. I apologize. If I make a choice, right? So to show that that's little o of epsilon squared, I need eta cubed over epsilon squared to go to 0. Or in other words, I need eta cubed, right? This term here, eta cubed over epsilon squared. I know that this one is going to be, if that one is going to be, eta cubed over epsilon squared has to go to 0. So what do we need? So I'm going to suppose eta is some power, and then let's see what power works. Questions about that? Okay. So we know that we have to have 3 alpha minus 2 greater than 0, so 3 times alpha minus 2, that's where that's coming from, has to be greater than 0 so that this goes to 0. So 3 alpha minus 2 has to be greater than 0. So alpha has to be greater than 2/3. So what works? We can use 3/4 in this case. So remember what we're doing now is we take n. So the top is n plus 1, and the bottom is n plus 2. So that pattern still works for our matching. And of course, these lower order ones are not going to be possible anymore. So this is the one that worked for order 0. This is the one that worked for order 1. Order 2 is requiring something a little bit more. The funny thing is we do all this work, but we don't gain anything in the asymptotic approximation. But we still need to show that everything matches so that we know for sure that that's the next composite solution. Okay. So this is our matching term right here. And of course, it matches exactly with what we have for the inner expansion.
You need an epsilon squared and the equation of there and order. There's that order epsilon.
That should be order epsilon squared, right? Just like here, it should be order epsilon squared. Little o epsilon squared as epsilon goes to 0. Does everyone or everything else look okay? Sure. I think it is. But so with this ansatz, we're taking now alpha to be 3/4. N plus 1 over n plus 2 still works, where n here is equal to 2, and we get this. Okay, so now clearly again, our matching terms agree, and so we're basically done. We form a composite solution for order 2 plus 2. The thing is, again, we're not improving. That's because, and you might not know it at the beginning or a priori, but you're already doing as well as you can possibly do. So let's talk about the width of that matching scale. So if we continue the process of matching in the prototype problem, so I claim that if we choose, or if you believe what we said before, eta is always going to depend on m and n. Here in our matching procedure, n equals m, so we can drop the dependence of m. That's redundant. So we suppose that we can, or we choose eta to be some power of epsilon. That's the most common thing to do. Why would you do something else when you could do something simple? Then it turns out that alpha n, what works is going to be n plus 1 over n plus 2. Okay. I'm not sure why I wrote this, but I guess we're just saying that it was bigger than the previous one. Okay. Bigger than the previous scale. So, of course, you can verify this for n equals 1, n equals 2. So this guy is going up to 1 as n goes to infinity. We just said that, right? Therefore, if I take for fixed epsilon, okay, so you have to fix epsilon when you do this little calculation, then the difference between those scales starts to collapse, right? The scales is here. So this is like epsilon. Okay, so which one's bigger? In whole number terms. So this guy's bigger, right? That's your delta scale. So this is a positive number, but since alpha n is converging to 1, this number is converging to 0. It's getting squashed to 0. All right, so the big question remains, why does the width of the matching scale diminish over, as we increase and increase? So this is a good question, and one that's going to have to wait until I think chapter 5 or 6, something like that. Has anyone looked at the notes lately? That they get longer and longer as we go because I'm furiously typing offline to keep ahead of you guys by a week or so. So, or to keep ahead of class. And right now we're I have typed up chapter 3, which is where we're going to go next time. So that's going to be asymptotic expansions for integrals as a parameter gets larger and larger. So for large parameters. The first thing we'll discuss in there is the method of integration by parts. That method may actually be useful to you in one of the homework problems. I'm not exactly sure. Maybe a simpler technique that we use in chapter 1 will be all you need for that integral computation. So we're going to cover the basics there. The first one being integration by parts technique, which you haven't seen yet. So that's a nice new interesting technique for getting asymptotic expansions of integrals. The next couple of techniques that we're going to look at go by the name of Watson's lemma and the Laplace method, and the method of stationary phase. Then we're going to do a little chapter on contour integration from complex analysis. So if you've never done that before in your life and you're kind of fearful thinking about what that might be, we do a full review of all that we need for that. And we'll even do a lot of examples to make sure everyone's comfortable with that. And then we'll do what's called the method of steepest descent and the saddle point method. So those are 2 chapters dealing with asymptotic expansions of integrals. And then we'll come back to boundary layer theory, asymptotic expansions of boundary layer problems that arise from boundary value problems. All right, so I'm done for today, a little bit early. Does anybody have any questions? Anyone at home have a question? If not, then I'll see you guys on Tuesday. I did want to point out another announcement. I have made up a office hour. It's on Fridays at 10 a.m. So the Zoom link can be found on so if you follow the Zoom link on Canvas, you should be able to find that. It's 10 a.m. on Fridays. So you can come in and ask about homework questions or let me know what you think about the course or what you're struggling with, whatever. I will and do always encourage you, if you find errors in the lecture notes or the lecture slides, please don't keep those to yourself. Let me know and I'll be happy to accept them and make the changes and update the slides. If you have been joining synchronously or asynchronously via video, I suggest you use the videos on YouTube because they're not as, I won't say the quality is higher than the Zoom videos, but the Zoom adds a few extra minutes of time at the beginning of a video inexplicably, and sometimes, well, only at the beginning. So sometimes there's 10, even 15 minutes of blank time at the beginning of video. So when I post them to YouTube, I chop that off. So if anything, you save yourself having to skim through the video and find out where the thing actually starts. Okay. So those are all the announcements I have. If you have any questions, you can feel free to send me an email. And otherwise, I'll see you at office hour or on Tuesday. Have a nice day. So, okay, good question. The question is, when is the homework due? I put the due date for 2 weeks, but I'm very flexible on the due date, especially if you're due to LaTeX, and it's going to take you a little while to learn that. If you get it in a few days after that, or even a week after that, should be fine. Right now, it's set for 2 weeks from today. I believe. Can someone double check that? Is that what it is? Yeah. So 2 weeks from today.